Hey everyone, when working with HuggingFace Transformer Pretrained model, one of the fundamental technique we use in most of our project is that we take the body or base model and then on top of that we add a task specific head to finally build our model. So in this video, we will see an example of that architecture because the same architecture will need to be applied in many projects involving pre-trained transformer model from HuggingFace. So when we switch from the pre-training task to the downstream task, we need to replace the last layer of the model with one that is suitable for the task. This last layer is called the model head. It's a part that is task specific. The rest of the model is called the body. It includes token embeddings and transformer layers that are task agnostic. This structure is reflected in the transformer code as well. The body of the model is implemented in a class such as BERT model or GPT-2 model that returns the hidden states of the last layer. And to get the hidden state of the last layer, we do something like this. That is output, we take the 0th element that's equal to my last layer. And the hidden state are passed as inputs to the model head to produce the final output. HuggingFace Transformer provides a different model head for each task as long as the model supports the task. That is, you cannot just use DistilBERT for a sequence-to-sequence task like translation because DistilBERT is not a suitable model for sequence-to-sequence task. And then we have task-specific models such as BERT for masked LM or BERT for sequence classification, which uses the base model and add the necessary head on top of the hidden states. For example, DistilBERT for sequence classification is a base DistilBERT model with a sequence classification head. The sequence classification head is just a linear layer on top of a pooled outputs. And similarly, for question answering task, you would use DistilBERT for question answering class, or which is a model head. The question answering head is similar to the sequence classification head, except it is a linear layer on top of the hidden states output. And so in this video, I will use a particular dataset from Kaggle, the link of which is given here. It's a news sarcasm detection dataset in Kaggle, and then I will take a base model, and then on top of that I will add a classification head. And the base model in this case will be DistilBERT base uncased. And so the first thing is just a regular step. I am importing all the necessary modules from HuggingFace and also from transformers. Specifically, I am importing these load dataset from the HuggingFace datasets module because I want to structure my dataset according to HuggingFace, following the HuggingFace structural pattern and the dataset architecture. Then because I'll be using PyTorch, so I'm just importing the necessary modules of PyTorch. Okay. Now the important thing is I have already downloaded this dataset into my local directory, so I'm just defining a root path for the dataset. It's a JSON file, so I'm just defining the path of that and then reading the dataset with pandas. Read JSON. It is no more read CSV because it's not CSV, it's JSON file, but you can read it as easily as any CSV file. So we can see this dataset structure right now. That is a JSON file right now is structured like this. There are 3 columns: is sarcastic, headlines, and article link. So for our case, for our exercise in this video, this article link will not be important, and the 2 important columns are the headlines of the article and the classification of the labels, whether it's sarcastic. In that case it's a 1, and if it is not sarcastic then it's 0. And that's a whole purpose of this exercise is to predict, given a headline, whether it's sarcastic or not sarcastic. And that's why I am building a classification model on top of DistilBERT base uncased to predict the classification of a particular headline. So basically here I'm just loading the dataset with HuggingFace load dataset. So just note the special pattern that I'm using here. So you pass the load dataset method, which I have imported at the top. And because I'm reading JSON data, so you have to mention JSON here, and then also mention your data files. In this case, I'm just passing the path. And next, I'm just removing column article link because that is not important for the exercise here. And also, I'm setting the format to be pandas, and importantly, because Hugging Face dataset are all split into three sets, that is train, validation, and test. So here I'm defining with this line the train part, and we will be splitting the dataset into validation and test in a second. And first, just some basic pre-processing on the dataset. I'm dropping duplicates from the headlines column. Then I'm doing a reset index with headlines and labels. And then I am also applying from pandas on my initial dataset HF. And then that's the important part here, which is train test split, test valid split. Yeah. So initially, I'm just taking a 20% from for test size by doing this dataset.train test split, and this method is coming from scikit-learn. And then further for the test set, I am dividing it again equally, that is 50% between between test and valid. And finally, after doing this, I will have a clean dataset dict following Hugging Face dataset dict format, which is train, test, and valid. So all I'm doing here in this line, from train, test, valid, I am taking the train for my train, test. From the test valid, that is from this, I'm taking the test, and for the valid part, sorry, here I need to make a little change. No, actually I'm right here. So note the difference between this first train and this train. Here, the train part I am taking from train test valid, which was defined in this line, and that will take 80% of the dataset. Now for the valid part, I am taking from this test valid only the train part, and that's my validation. So actually test valid is already only the 20% of the original dataset. From that, this train will take 50%. That is actually 10% of the original dataset is for valid. And now finally, I'm just printing this dataset HF, and that will print a nicely formatted dataset dict, which is what Hugging Face datasets follows. And we can see the splits here: train, test, valid. And for my train, I have 22,802 number of rows. For test, I have 2851 rows, and for the valid, 2850 rows. Awesome. Yeah. So now a quick reminder that this DistilBERT base uncased. In this model, DistilBERT base uncased, each token is embedded into a vector of size 768. And the shape of the output from the base model is batch size by max sequence length by embedding vector size. And max sequence length is also capped for a particular model, and embedding vector size in this case is 768. I need to check. I think DistilBERT base uncased, if you can go just Hugging Face documentation to check what is the max sequence length. I think it is 512. And that's what I am using in the next line as well. So the first thing, I need to tokenize a batch. So I'm defining a tokenize method here. It will just use my tokenizer and pass it the batch headlines part, because headline is my column names, and truncation to true, and max length 512, which is what the max for DistilBERT base uncased. And then my tokenized dataset is just you take your dataset HF, which is this one that we just created, dataset HF, and apply the map method. This map is coming from Hugging Face Hugging Face datasets map method, and this is a very powerful, very useful method. It will apply this tokenize method here on each row across the dataset. And obviously, this tokenizer is coming from the tokenizer defined here. It is the tokenizer corresponding to my model checkpoint, which is DistilBERT base uncased in this case. So I'm just doing auto tokenizer from pretrained and passing the checkpoint. Very standard, very boilerplate code here. Nothing, no complexity right here. And tokenizer.model max length, I am defining 512. All right. So at this point, my dataset is completely tokenized and I am just printing the tokenized dataset, and that should give me the similar structure here. Only thing is that after tokenization, I have some new things or new features added to my dataset, which is input IDs and attention mask. We can see these new columns added to each of my train, test, and valid input IDs and attention mask. Very important because these two will be the input data or input parameters to my model based on which the model will predict. Yeah. And now, before proceeding to build my custom model, I just need to do another pre-processing kind of thing, which is use a set format method from HuggingFace to set the dataset format to be compatible with PyTorch. So, tokenized dataset. I mentioned torch. I also need to mention all the columns, which in this case will be input IDs, attention mask, and labels. And then I need to define the data collator. I have already imported at the top data collator with padding. So the data collators are objects that will form a batch by using a list of dataset elements as input. These elements are of the same type as the elements of my trained dataset or eval dataset. To be able to build batches, data collators may apply some processing like padding. Some of them, like data collator for language modeling, also apply some random data augmentation, like for example random masking on the formed batch. So data collector automatically actually pads some model inputs in a batch to the length of the longest example. This bypasses the need to set a global maximum sequence length and in practice leads to faster training since we perform fewer redundant computations on the padded tokens and attention mask. And now with that, I need to construct my task specific custom model class that inherits from the that will inherit from nn.module, that is PyTorch's nn.module. So I need to define this class here. Let's zoom out a little bit. So this is my custom model actually, and that's why I'm naming it to be explicit, my task specific custom model. In your case, whatever the task, you name it like that. For example, if you are building a classification, you can name it as my classification custom model, just for example. Here, this is an example exercise, so I'm just building my task specific custom model for the naming. It's inheriting from an nn.module. And also note that in this case, I'm using DistilBERT base uncased, but actually you can use any model in this example, not necessarily a model trained for classification, since we will only use the model's body and leave the head. Head is something we will add. So you can use many other models as well for your base model. And within super, Now I'm going to load the model with a given checkpoint and extract its body. Self.model equal to checkpoint, which will be the name of the original model path in HuggingFace. From checkpoint and tension equal to STAT. Okay. And now the new layer that I'm going to add. So before this line, that was my body of the model, and now I am going to add my new head. So self dot first a dropout layer, and also as an ending layer, I'm just going to add a single classifier layer, and that will be a fully connected linear layer. And here you can actually, for depending on your situation, you can actually build out your complete layer. It can be an LSTM, it can be other model, other layers, it can be multiple layers after layers, whatever your plan is. So in my case, this is a simple linear layer. This is in features, which is 768 dimension, and num labels. So the first argument to nn.linear is in features, which is the size of your input samples, and the second argument is your out features, which is the size of each output sample. And just to explain a little bit about these nn.linear, this line of code. So, for example, you define, say, self.hidden equal to nn.linear 784 by 256. It means that in your neural network, this is a hidden layer. That means because it is hidden in between one of your input and output layers, and it is also a fully connected linear layer which takes input of shape batch size by 784, where batch size is a number of inputs which are passed to the network at once, and transforms the input by the linear equation of y equal to wx plus b into a tensor y of shape batch size by 256. So I can just write it here, something like this. So this is what it means, that self.hidden will just transform the 78 batch size by 784 dimension input tensor to a tensor which is of shape batch size by 256 dimension. Anyway, that was only for explanation. Let's delete and let's continue with our class. So next, I need to write my forward function. Yeah. This is the main two inputs to my transformer. Labels equal to none. So first extract outputs from the body of the base model, which will be outputs equal to self.model, and to that I pass input attention mask. What else I need to, yeah, that's it. And now after I got the body, I need to get the custom layers. So first define the last hidden state, which is last hidden state is always outputs. Take the 0th element. That's my last hidden state. And now from this sequence outputs will be equal to self dot, sorry, yeah, self dot, because I have dropouts. To that I pass the last hidden state, and then the logits. Sequence outputs, and take the everything from first dimension, 0 from the next dimension, and everything from the third dimension. First dimension is inferred, and that's why -1, and the second dimension is 7, 6, 8. Because that's what we defined here. Now calculate the losses. Loss function is nn.cross entropy. It's a binary classification problem. Cross entropy loss. logits.view. Enables. Finally, returning from the forward method is a token classifier output. We already imported the token classifier output at the very top. So loss is equal to, oops, what happened? 1 second. Loss is equal to loss outputs hidden states tensions here. And to understand more about this token classifier output, this class, we can look into the official documentation in HuggingFace. So all models have outputs that are instances of subclasses of model outputs. Those are data structures containing all the information returned by the model, but that can also be used as tuples or dictionaries. Let's see an example from transformers. Import BERT tokenizer, BERT for sequence classification, import torch, and then I get the tokenizer outputs, model inputs. Okay, let's look into our ones, which is so these are all these output classes. For example, they have base model output, they have base model output with pooling. What was our name? Our name was token classifier output, and So this is my token classifier output. It takes loss as a first argument, torch.float tensor of shape 1 optional, and then it takes a logits classification scores, hidden states, attention. Let's go down. Hidden states, which is also a torch.float tensor, and attention. True is paused or when config.output attention equal to true, tuple or torch. Attention weights after attention softmax used to compute the weighted average in the self attention heads. Yeah, so we have already passed all these arguments here: loss, logits, hidden states, and attention. Okay, so remember these attention mask, this particular parameter we supplied here, the significance of these, because this argument indicates to the model which token should be attended to and which should not. So if attention mask is 0, the token ID is ignored. For instance, if a sequence is padded, to adjust the sequence length, the padded words should be ignored, hence their attention mask is 0. All right, before starting off the training, I need to do another thing, which is create a PyTorch data loader, because that will have the responsibility of supplying batch by batch data to during the training. So from data import data loader. And it takes, I have to pause the train here, train part of my tokenized dataset. Oops, tokenized dataset. Shuffle equal to true. Collate function will be my data collator that we have defined earlier. And I have to do the same for the validation part. Other things remain same. I also, for the validation, I don't need batch size because it is only for evaluation, no training. Okay, now get ready to start the training, but just define a few parameters for the training. Transformers, import Adam W, which is my optimizer, also get scheduler, scheduler. Yeah. What else do I need? I need to define the optimizer, which model task specific. Oh, I did not define the model task specific yet, so let's do that before defining all the parameters. So first define the device, just regular code. If CUDA is available, use CUDA, otherwise CPU, and then model task specific would be checkpoint equal to checkpoint. I have only 2 labels, and then transfer these to device. Cool. To the optimizer, I need to pass the parameters of the model. So what does the documentation say? The params. Yeah, the first one is nn.parameter.parameter, iterable of parameters to optimize or dictionaries defining parameter groups. Yeah, so model.parameters. Define my learning rate as well. And number of training steps would be epoch multiplied by the length of the train data loader. So num, right. Okay, and I need to define Euler scheduler. For this baseline, I just want to keep the number of warm-up steps to 0, so I do not need a warm-up steps actually. Okay. Yeah, that's cool. Okay. Next, for the metric definition for the evaluation, I need to import the load metric from datasets. My metric is F1 score. And now finally, actual training. So this is where I'm going to train my custom model. So first import UDM. Training steps. This will be number of people. For key value in batch.items. Supply the model with the batch. Outputs. And also backward propagate your gradients. Optimizer tab. Update the optimizer. Skip. And after this, zero your grad. So train. Okay, now evaluation. Task specific. batch is equal to because I'm in the evaluation, so I need to use a context manager of torch.noGrad. And the predictions will just be equal to torch.argmax. It's the probabilities, and I need to get the max probability. So from the logits, I get the max probability across the last dimension. And now time to calculate my metrics, because I have both the actual and also the predictions. And because it's a batch by batch calculation, I need to use the add batch method here. So metric.add batch. Progress bar eval. Okay, I should print my metrics here. Metric.compute. PUT. Okay. And next is the post-training evaluation. And that code is rather very simple. So first, model task specific.eval. Now I need to get my test data loader, which is loader equal to data loader tokenized data set. From that I take the test BERT. Or sorry, that is key value. Okay. The structure of code is pretty much the same that we used in the training. So that's my batch, and then I need to define a context manager with torch.noGrad. Output specific logits. Prediction says torch.argmax, just like previously. Across the last dimension. And now metric calculation, metric dot add. So I'm just reading the documentation of metric dot add batch of predictions and references for the metric stack. Predictions are the predictions, references are the actual references, and both are list, array, or tensor. Yeah, that's what I'm doing. Oh, so references is my batch labels, because that's the true value. Okay, at the end, just print the metric.compute. So this is the result that we got. So during the training, our F1 score was coming like this. During the training part, that is when we are going epoch by epoch for the batches, and then for the post-training evaluation on the test data set, the metric.compute finally produced a rather very good why it's not coming, a rather very good F1 score. Let me of 0.923. That's my final F1 score on the test data set. So to sum up, what we did is we took the base body of the base model from HuggingFace Hub, and the name of the model is DistilBERT base uncased, and then through these custom class, we added a single linear layer, of course, with a dropout as well. That is our head. And that's how we added the head to the base body of the model and created this whole class. And that whole custom model we applied on the data set to predict 0 or 1, that is a binary prediction of our sarcastic news headlines data set. And the final computed F1 score was rather good of 0.927. Alright, that pretty much wraps up this video. If you have liked this one, smash the like button. And also do subscribe, because I'm going to do many interesting NLP projects over the coming days and weeks. So see you in the next one. Thank you very much for watching.